More than let's start with this.
कुछ इंट्रोडक्शन वगैरह देना होता है लाइक
Direct start.
इज रिकॉर्डिंग वेरी श्योर मतलब कुछ इंट्रोडक्शन वगैरह नहीं देना था
नहीं.
सो So basically, this topic is ideated from my attendance at ICTS recently, and so there I had an opportunity to experience the lecture series in optimal transport theory. So that lectures were given by Professor S. Balakrishnan from Carnegie Mellon University. So like I'll cite the resources which I have used. So so primary reference which I'll be using is Stat Optimal Transport by Sino-Chiri and Riverent, and yeah, so that's all. So these are the primary references I have used for learning OT as well as explaining the OT here. So as a first talk in OT, I don't aim to enforce any abstract notions like going deeper into analysis or the abstractification of this probability theory part, but what I aim to do is to basically give heuristic explanation for every statement I give, and the background about OT and how it basically changed the landscape of this statistics and probability. So I'll start with a high-level remark about optimal transport is that optimal transport is basically a framework which studies the notion of distances between probability distributions, and that distance in itself carries a notion of like it carries mappings between those distributions and which respect the underlying matrix structure on which the distribution is being imposed. So with that thing, and also that these have some interesting properties and that it has various applications, some theoretical applications to PDs and convex analysis and stuff. So my plan for this talk is about classical formulations of OT, the classical formulations of OT, and then basically there are two of them. We work on linking these formulations we'll see about Wasserstein distances, and ultimately, if time allows, we'll also see some duality aspects. So the broad purview of this talk is about probability and optimization, because this optimal transport theory is also well embedded in the study of probability and optimization theory. So duality is basically arising from optimization techniques. So that was the stuff which I have planned to do. So yeah, so classically in late 18th centuries, Monge came up with a formulation what he said was, so you have a pile of sand, you have a ditch, you want to transport all the sand particles into this ditch. And obviously, like, since the volume are same, then we can normalize it to 1. So volume is 1. That is our area under this curve. Like, if we say this as a distribution mu, this as a distribution mu, like flip it and it has a distribution mu. So he asked, what is an efficient way to transfer this pile of sand into ditch? So he gave a program, like so like all these sand particles, if we abstractify these notions as, so these sand particles are embedded in RD, a d-dimensional real space. So he said, like, associate a map, the transfer map or transport map, RD to RD, which takes the sand particle, transforms to T of x. So he said, like, how can I optimize, like, the cost associated with transferring these particles from the pile of sand to the ditch? So by cost, here I would mean the distance traveled by the sand to this ditch. So ultimately, for the sake of simplicity and analysis, we can use L1 Euclidean cost. And so yeah, cost of x dx is equals to N1 norm of so that's the cost. So what he said, that T should have a valid condition, which is T pushes mu to nu. So what do we mean by this intuitively is, I have mu, like this. So let's say it is A. So T inverse of A, let's say this. So he said, like, so basically T hash mu equal to mu means mu of T inverse of A equals to mu of A. That is basically T push mu equal to nu. So he said that if we are having a transport map from RD to RD, it should be a valid map which follows this T hash mu equal to nu. So there arises some particular questions to ask. Like, first of them is, does this T always exist in this sense? And if so, how to characterize them? Are they stable? Are they regular? Or are they unique? So we can tackle this question one by one. It seems that these are not true. Like T does not always exist because in a discrete case, see a point mass.
So mu and your functions defined on RD.
No. So mu and nu are measures.
Okay.
So a distribution on RD. So let's say x is a random variable distributed as mu, which is in RD. So it's a probability distribution on RD. So like on RD you can have a collection of measures, like, and mu is a part of this. Yeah. So you can have like many probability distributions on RD, and mu is one of them. Mu is one. So we are basically dealing with RD to RD, but there may occur a case like if you go much deeper into it, you may have a transport map from Riemannian manifolds to a Riemannian manifold. So yeah. So first question. So if you see a point mass, let's say at 0, it's a point mass. Mu is at direct delta at 0, and nu is half times of delta minus 1 plus delta 1. So intuitively, if you try to see a valid transport map which follows this, you may not see any of the valid transport map, because if t of 0 has to be transformed to t of 0 in a deterministic map, it should take only one value. But here what it is, it takes 1 with probability half. It takes -1 with probability minus half, like half. So it's a Markov kernel. So what is it? Like it's basically t of x to p of y. Like it's all the measures in y. So like you have a space x and it goes you have a space x and it goes to probability distributions on y. So basically it is a probability distribution. So it goes from RD, 0 goes to this thing. So it's not a deterministic map, and hence it fails to follow the criterion of t hash mu equal to nu. So this first question is, it does not always exist. So eventually it fails to ask the other question, like how can we characterize? But yeah, in some of the cases it do exist. So until late 1950s, this study of optimal transport was very dormant because nobody knew how to tackle this kind of problem, how to find a transport map which is valid, which transforms mu to nu, any mu to any nu. So Kantarovich came up with his own formulation in a classical 2-page paper. So it was a 2-page paper which just transformed the understanding of optimal transport. So then came Kantarovich. He gave a formulation that instead of looking about a transport map, a valid transport map, what we can do is just study about valid joint distributions, or say couplings between mu and nu, two measures. So what he said was, let gamma be the coupling between two measures, mu and nu. So it's essentially a joint distribution over mu and nu. So which follows the condition as gamma of A cross RD, the marginal, the first marginal is mu, gamma of RD cross A, the second marginal is nu for all Borel A. For all. So he gave this formulation. Now, in Monge's case, what he said, if I had a map T exists, then the optimization problem T is argument, like the minimizer of this cost over all T. So let's say T naught. But we saw that T always may not exist. So what Kantarovich said, so yeah, first of all, we have gamma mu nu is a collection of all such gammas. So Kantarovich said the optimization problem is gamma star is equals to the minimizer of overall gamma x cross y, cost of xy d gamma of x. So that was Kantarovich's formulation, and again we can ask these same questions as in the case of Monge. So in this case, it always exists because it can be easily seen that the simplest form of coupling is independent joint distribution. So like gamma of A cross B equal to mu of A equals into mu of B. So this particular gamma lives in this particular gamma lives in this whole collection. So gamma mu nu is not empty. So there always exists a particular coupling, but it may not be the optimum. So also one of the problem in Monge's formulation was the constraint, that is T hash mu equal to nu. It was neither linear neither convex, because in our case, as we'll see, that linearity and convexity of the constraints and the objective is this. So linearity and convexity in the objective and constraint is very primal to us. So in this case, T hash mu equal to nu, we can see that it is neither convex, it is neither linear. Convex, it's not convex because to nu. So it is not convex because if you have any t lambda, which is convex combination of t1, t2, let's say t1, t2 exists. So for lambda belongs to 0, 1, t lambda equals to lambda t0 plus 1 minus lambda t1. So if t0, t1 exists, t lambda may or may not be, may or may not exist. Like, we cannot say. So yeah, so that proves non-convexity. And for non-linearity, the t hash mu, by its very definition, it means that for any nice, let's say, phi y to r, where y is rd, for any nice phi y to r, that is the very meaning of this thing. So as you can see that phi is composed with t, that in itself takes away the linearity of this thing. So it's non-linear in this case. But what happens with Kantarovich's formulation? In Kantarovich's thing is, what it's happening is, so first see, it is convex. So let's say gamma 0, gamma 1 exists, and gamma lambda equal to lambda times gamma 0 plus 1 minus lambda gamma 1. Now we know gamma lambda equals to lambda times, we know that gamma 0 of A cross RD equals to mu of A. Same with gamma 1 of A cross RD equal to mu of A. So gamma lambda of A cross RD is just mu of A again, because it's a lambda 1 minus lambda thing. So basically, and same thing you can say for mu of A. So essentially, gamma lambda is also following all the criteria which we had for gamma. For linearity, it's easy to observe. Let's say J of gamma equals to C of xy, that is cost, d gamma of xy. Now, if I say g of a gamma 1 plus b gamma 2, it is just cxy d a gamma 1 of xy plus b gamma 0 of xy, 2 of xy. So the integral splits, and we eventually have a times j of gamma 1 plus b times j of gamma 2. So it's linear in this case. So we have in Kantarovich's formulation every nice thing which we didn't have for Monge's formulation. So till here it was going nice. So maybe what we can do is, before we go to linking these two formulations, like at what time they intersect, we can look at a particular discrete case for the Kantarovich's thing. So maybe we can look for a Kantarovich's example, like how the optimization problem in this case is being solved, and also a case where Monge's formulation is also agreeing with the Kantarovich's formulation. So on a side note, I must say that the optimal transport field, like the field of work in optimal transport theory, is constantly evolving, and there's some collaboration which is known as Kantarovich Institute, Kantarovich Initiative. It's basically a collaboration between many American and Canadian universities, which basically deals with OT plus X. X is anything like where optimal transport can be applied to or can be used to enhance the methodological study of that field. So if you guys are interested about going through this thing and exploring new things about OT and its application, I must say that you can look at this site. So yeah, back to our example in discrete case. So let's say our mu is so we have these two mu. Each have equal weights associated with every point xi, yj. So let's say a case of 4. So x1, x2, x3, x4, y1, y2, y3, y4. Each has its own weight, 1 by n everywhere. Of course, like you can have n not equal to m for x and y, but we are dealing with a special case to just illustrate about the linking between Monge's formulation and Kantarovich's formulation, and also seeing the Kantarovich's formulation in action, that how we arrive at a specific coupling gamma and a map also. So what happens in this case is first of all, so Cij basically is this thing. X is I, Y is J. So this is the objective, and we have the constraint as these are the constraints, and it's a constraint optimization problem. As we can see, the constraints are convex and are also linear. So what happens is this gamma ij, it is n cross n matrix. In this case, it's a 4 cross 4, because gamma ij's are basically the joint distribution of pair of particles. So like it occupies n cross n places, n cross n values, hence an n cross n matrix. So it's an n cross n matrix. So your capital gamma mu nu is basically R n cross n positive, and so these two constraint sets basically imply that up to a scaling of one by n, the gamma matrix is a doubly stochastic matrix. What do I mean by that? Is every row sums to 1 by n and every column sums to 1 by n. Like usually in this case it's 1, but we are scaling it by 1 by n. So every row and every column sums to 1 by n. So now what do we have is a Birkhoff polytope. What is this? Polytope, if it's a jargon for you, then it's a convex polyhedra for ease of understanding. So Birkhoff polytope is collection of all matrices M such that M is doubly stochastic matrix. So Birkhoff polytope, you may say that it's a polyhedron and its vertices are a permutation matrix. Why so? Because Birkhoff polytope in itself is a convex hull of permutation matrices. So like these are the examples. It is a permutation matrix. So we have all of these permutation matrices and the convex hull of that thing, which is the convex combination of these things, is a Birkhoff polytope. So this Birkhoff polytope has its vertices as permutation matrices. Now it is a linear program, and it's a high school fact that linear program takes its optimizers as one of the vertices of the convex polyhedron. Like in a case of two lines intersecting, if the constraint set is this shaded region, then the optimizers with respect to this constraint is along one of the vertices of this shaded area. So the linear program, because all our constraint and objectives are linear, it allows us to infer that our optimizers are on the vertices. Like the optimizer is one of the vertices, and that is one of the permutation matrix. So what do we infer from that? That particular gamma, the optimizer, which is a permutation matrix, it just basically matches x1 with some y3, x2 with some y4 and stuff. So a particular permutation is allowed, and that is a deterministic map. So we see that through Kantarovich's formulation, we are able to arrive at Monge's thing. We are able to find a valid map, which just basically permutes the points in x to y. And that was a particular example of how this optimization problem deals within a discrete case for this thing.
Also, what do you mean by a vertex being a permutation?
Okay. Permutation matrix. So basically, Birkhoff polytope is a convex hull of permutation matrices.
How do you think about it?
Huh?
How to visualize it?
How to?
Is it possible to visualize that?
No,
Like
no.
it's
It's just algebraic notion.
okay.
So we are just using the geometric inference of algebraic notion to arrive at this thing that this linear program is optimized. And yeah, so now basically we can look to link these two notions, the Monge's formulation as well as Kantarovich's formulation. So here we see that they two were agreeing with each other. Also, prior to going forward with linking Monge's and Kantarovich's formulation, I would like to introduce the key notion about Wasserstein distances, which are very primal in the case of optimal transport theory, because Wasserstein distance is that statistical distance which is a measure between the two distribution mu nu, and like how mu is being transformed to nu, what is the notion of distance between mu and nu, two measures. And this Wasserstein's distance has some special properties attached with it because it also respects the underlying matrix structure of the space where the distributions are defined. So Wasserstein's distance is noted as WP. So for that case, we have an LP Euclidean cost. It's the pth moment of Euclidean norm, the normal Euclidean norm, L1 Euclidean. Yeah. So it's a pth moment of the L1 Euclidean norm, and using this as the cost, WP is defined as R min minimum distance. So this is the Wasserstein distance. Now the interpretation is Wasserstein's distance is the best cost in this case. So the best cost is associated to a notion of distance between two measures primarily. And so first point, that WP satisfies property of matrix, and the other property, that WP respects the underlying matrix structure so WP respects the underlying matrix structure. So to illustrate about that point, like the first point is easy to visualize, like you can plug in the integral and see it yourself that it follows the matrix rules. The other point, to visualize it as, so say you have 2 points. So you have at 1, -1, 1, and take this as mu. Now for nu, you take it as -1 minus epsilon, 1 plus epsilon. You just perturb a little bit. So ideally, the distance between these things should not blow up. Like these are just small perturbation of original mu. So so in domain of broad, like in broad domain of statistical matrix, we have total variation based matrix, we have KL divergence, Kullback-Leibler divergence, we have chi-square matrix, we have Hellinger's matrix. These are some statistical matrix which are there, but the problem with them is, like, I don't need to give some explicit form of these matrix, but if you see my total variation matrix, these two have a distance of 1. KL divergence blows up to infinity if you perturb this mu to mu, and same with the case in this. So in the case of Wasserstein P matrix, let's say 2 equal to 2. Wasserstein matrix, it is just if you plug these things in this, you'll have Wasserstein matrix is less than equal to epsilon square. So it basically respects the underlying matrix structures of this RD, that if you perturb your measure by epsilon amount, you should not have a blow up in the distances of these two measures. So that's why it is a very nice structure matrix on the space of probability distributions. So yeah, now we can look to basically linking Kantarovich's and Monge's formulation after having understood what about the
You have
Wasserstein.
defined WP like that, no?
Yeah, the WP
It's a metric.
is a best cost
Okay.
of transforming the measures. So it also follows the metric rules, which we have the triangular inequality, the positive part, and the two which I illustrated as that it respects the underlying matrix structure where the measures are defined. So that was about it. Now, with understanding about Wasserstein matrix, we can look toward linking these two things, Kantarovich's and Monge's formulation, in a continuous case rather than discrete case. So what we have is a classical theorem, Grenier's theorem. I may not delve deeper into this proof because that's not the aim of this talk, but to give heuristics about this proof, how it impacts our understanding about how Kantarovich's and Monge's formulation are linked.
Excuse me.
Huh.
I'm sorry to interrupt, but it is written that it is first year, second year, third year. I don't understand anything.
Because you joined in mid, so
Yeah, but I think even if I join it starting, I
what
just
you didn't
understood
understand?
that
What
part.
part?
I just understood that part, high school part.
This thing? Okay. So in the case of measure, you just see it as a normal integral. It may not be very nice explanation to it, but you just take it as a rules or statements, maybe, if you are able to follow that. The further understanding of this, you are not able to follow. So were you able to follow the Wasserstein matrix? No. The integral part also. So maybe like I can write infimum over all gamma.
I don't know what that is.
Infimum.
Infimum and that and
Oh.
double digit lines.
Gamma, capital gamma defined earlier what couplings are. So these are basically joint distributions. Such that gamma of A cross RD. You know what a joint distribution is? No? It will be very difficult to explain about joint distribution right as of now because maybe if you can try to follow what I'm talking about, it would make sense because I'll give heuristics about what happens, and if you wish, you can reach out to me later after the talk, and I can brief you about some resources which you can.
Can you just tell me what those double lines are before X?
Oh, it's a norm. So like it represents the norm. Like the distance, like in a Euclidean space, it's just the distance from the origin to X. The Euclidean distance. So the Brenius theorem is basically, let's say if you have P equal to 2 in the Washer-Fries matrix, you have P equal to 2, and in this case, if mu and nu have finite moments, what do we mean by that? Oh, not mu. Yeah, mu. Second one. That is the meaning of finite second moments. Now, the other condition is mu. If mu has a density with respect to Lebesgue measure, mu has a density with respect to Lebesgue measure. Also, mu is absolutely continuous. Maybe I should write this. Lebesgue measure. But this stands for absolute continuity. So, what does this mean? Mu has a density with respect to Lebesgue measure, because in our understanding, mu is a distribution function, a measure, but it's not the PDF. So for PDF, so basically what we see that if omega, this is a probability space and x is a random variable from omega to r, then P is a, let's say, P composed with x inverse is a measure on R, which is a distribution on R, which is a distribution mu in our case, P composed x inverse. So, what do we mean by, let's say it is Px, and what do we mean by PDF? PDF of probability density function of Px is if Px is absolutely continuous to Lebesgue measure m, then PDF fx is Radon-Nikodym derivative of Px with respect to Lebesgue measure. So mu has a density with respect to Lebesgue measure. I mean this. A radon nicotine derivative. And mu is absolutely continuous with respect to Lebesgue measure is the primary condition for the radon nicotine derivative to exist, and that's the other part which people could appreciate about this statement. But nevertheless, if you have no background in measure theory, then it won't make sense. But assume that mu has a PDF. Not all distribution has a PDF, but if it does, probability density function.
What is that?
So you know about the bell curve, the Gaussians. So it is a PDF, like the probability density function, but the CDF or the mu in our case is this. So CDF is basically P of Z less than equals to X, where X is here. So basically the shaded region in this. That's the CD. That's the distribution function. And this bell curve is a density function. So abstractifying that. Okay. So if these are our hypotheses, then what Brainier's theorem claims is, maybe I should write the claims here. First one, a very strong result, which is, as in the case of Monge's formulation, the transport map T, there always exists a transport map T naught. Such that T hash mu equal to mu. Note that we have no restrictions on nu. Nu can be discrete, nu can be continuous, but we have conditions on mu. And the other part, which links Kantarovich's formulation to Monge's formulation, is that the coupling induced by this map, like how these points are being, like the points in the measure, this mu distribution are being, so in a measure theoretic way, I should write the transport map exists and is unique, mu almost everywhere. Just skip the notion if you don't have any idea about measure theory, but just after having a measure theory course, I should write it like this. And then another strong result is that this T naught is of the form of a gradient of a convex function, particular convex function of like phi naught. So this particular optimizer map is a gradient of a convex function, which is a very strong result, and we may look towards the heuristics behind it, that why this gradient of convex map impacts our framework.
What is gradient of convex map?
Gradient is basically grad f, like say f is a function on x, y, z, and grad f is partial derivative of x, y cap.
But this is gradient. So what is gradient of that?
So the convex map is just less in this case. Yeah. So like T naught is a gradient, like it's a vector. It's a vector map. So T T naught is a gradient of a convex map, and this, since T naught is unique, the P naught is unique mu almost everywhere.
P naught is a map from RD to RD, right?
Huh.
But
What does it mean for it to be a
Gradient is also map into RD. Like it's a vector map.
So RHS is a 3 vector.
it's a vector basically.
The gradient is a
So,
vector in RD.
What?
The
Gradient.
gradient phi naught will give you a vector. Right?
T is a map from RD to RD.
Gradient phi naught will give you a vector.
Hmm.
Right? You are equating a vector to a function.
So map is also
T of x is gradient of phi naught of x.
Ah.
So T naught x, right?
Yeah, T naught of
Arey,
x.
gradient is a map from a space to RD,
Oh, okay.
and T is also RD to RD. So the
Got it.
object space is same. So the coupling gamma induced by this map is also unique. So what do I mean by coupling induced map?
Just to be sure, that gradient means you're taking the partial derivatives of x1, x2, xd when evaluating at the input function, vector x.
Yes.
So gradient नहीं बोलते हैं.
तो क्या बोलते
I don't know what it's called. Gradient is just 3 vectors, right?
ग्रेडियंट कब से 3 वेक्टर्स हो गए?
Okay, sure. I have never seen 4D gradients.
Gradient can be any dimension, man. It doesn't matter. So yeah, the gamma, the coupling induced by this T naught is this, which is also unique with respect to T naught. So this Brenner's theorem kind of links Kantarovich's formulation with the Monge's formulation, because the notion of Wasserstein metric was from Kantarovich's formulation. We have an induced coupling from this T naught map, and hence we have the linkages between these two. So also additionally, there also exists a reverse statement to this theorem, that if you have the same conditions on the nu, then you eventually have a reverse transport map from nu to nu, which is a Fanchel conjugate of this thing. So primarily Fanchel conjugate, if nu to u you can skip it, but so if nu follows this thing, this earlier statement, then you have S naught, which transports nu to mu, and this S naught is gradient of Fanchel conjugate of phi naught, and it is defined as phi naught star supreme phi naught star of y is equals to supremum over x inner product of xy minus phi naught of x. Inner product, if you don't know, you can skip it. That's why I said you can skip the Fanchel co-conjugate part, but the aim was to just realize that if you have the same conditions on nu, then you eventually have a reverse transport map to that thing, S naught, and you also have a unique, that the same coupling is also being followed by the reverse transform, because it's essentially the same thing between mu and mu. V optimizing. So yeah, so just a small detour to why this convex gradient meant to us, or what impact it creates, is that it has some inherent relationship with monotonicity, or in sense we have a notion of multivariate monotonicity, which is cyclical monotonicity, which is very abstract to understand, but if you can understand it's fine, else it's just easy to wave it off. So convex gradient has something to do with monotonicity, multivariate sense because we are dealing in RD, but to illustrate it in 1D, we can see it as a convex map. So your tangent here, say y, say x. So basically what convexity allows us is phi of x, which is phi of x is greater than equals to phi of gradient of phi transpose y minus x. The same application to y is phi of x greater than ultimately we have gradient of so this in sense say that your gradient of a convex function in 1D is monotonic. Because if x is greater than y, the grad of phi x is greater than grad of phi of y, and vice versa. But in the case of multivariateness, we generalize this monotonicity to a cyclical monotonicity, which is if you have multi-parameters x1, x2, xk plus 1 is x1, then this kind of monotonicity is called cyclical monotonicity. And the particular condition which it follows is sum I equal to 1 to k xi minus xi plus 1 times grad phi of xi is greater than equal to 0. So basically it says that if you travel along this cycle, you have this sum greater than equal to 0. That is the sense of cyclical monotonicity. And if you imagine in a one-dimensional thing that what monotonicity implies on the transport maps is that if you perturb your original distribution mu by epsilon in the right direction, and so through this monotonicity you won't expect that your nu will your nu will shift to left. If you shift your mu to right, then your nu will also shift to right. If you shift your mu to left, then your nu will also shift to left. So that kind of property is very crucial for us in the case of OT framework study. And the other thing which primarily, like, how much time do I have? The other thing is about the duality. So basically, if you have learnt about duality in any aspect, like maybe linear algebra or something, we have dual spaces and all. So duality is just the thing, like in our case specifically, duality is just transforming our objective and constraints in a way that the primary goal of optimization remains the same. Like in this case, the constraint and objective is like infimum of the cost along that particular coupling, where the constraint is the first marginal is mu, the other marginal is nu. So in the duality aspect, we transform that particular objective and constraint to another objective and constraint, usually arising with the two notions of duality, which is weak duality and strong duality. Weak duality usually gives lower bound to our original problem. So the original problem is known as primal problem, and duality gives lower bound to the primal problems. Like so if it has a lower bound, the way it helps us is if we find a way to choose a candidate option for our original optimization problem, and if we see that it is not being followed by the lower bound, then we can easily eliminate that option. So basically it helps us to choose our own candidates for our optimization problem. And the strong duality is when both of the primal problem and dual problems answer just equates, so that the other inequality is also good. So we have upper bound, lower bound is equal. So that was about duality. And first time when the linear program was studied by Kantarovich through this optimal transport framework, he introduced the notion of duality in the linear program. So so maybe in linear program in a discrete case, if you have this thing, Cij and the same case, so basically we solve the dual problem. So our original problem was to minimize this thing, but now we look at a dual perspective, which is through Lagrangian method, which is we just give Lagrange multiplier to this alpha j, alpha beta I, and delta ij. So we have Lagrangian as alpha j, beta I, delta ij, gamma ij, gamma ij, cij, j alpha j, So this forms a Lagrangian, and the dual problem is min over gamma max over alpha beta delta all greater than equal to 0, Lagrangian of alpha beta delta gamma. So this is our dual, and if you want to see about how this min-max problem makes sense as a dual to a primal problem, it is as follows. Let's say it is f of gamma. So if we see our Lagrangian as here, and if we see that if these constraints are not followed, then it can easily be non-zero, and we can easily tune our Lagrangian multipliers anytime, and we can make this whole term blow up. So eventually this max of this thing is basically f of gamma if constraints are followed. And it's infinity plus infinity if not, because you can easily blow up any term and it's going to get to infinity. So ideally, and if we use min gamma here, it's basically minimizing this f of gamma ultimately. So that's why our primal problem is linked with this min-max problem here in the dual. And since our constraint and objective are linear, it's a min-max optimization problem on a linear program, hence strong duality exists. That's a primal fact which you can take for granted, and using that thing you can just swap the min and max, because the strong duality says that if min max of this is this, then max min of this is also equal to this. So you can just do max min of this, you can take the min of gamma, and here to take min of gamma you just need to differentiate this whole thing by gamma ij, which yields to this thing Cij minus alpha j minus beta I minus delta ij is 0. Because you are minimizing it, you take the partial derivative with every gamma ij and equate it to 0. So that's the primary constraint for the minimizing problem of this whole thing. So, oh no, not this. So we have transformed it as max min of Lagrangian. So evaluating this case gives the constraint for this maximum case, and plugging in this constraint to this again, and to maximize this thing, what we have is sigma j alpha j by n plus sigma beta j by n is equals to sigma Cij. Yeah, so Cij minus alpha j minus beta I delta ij is equals to 0, and this whole problem evaluates to max of alpha beta, and from here it is easy to evaluate that alpha alpha j plus beta I is less than equals to Cij. So this is the constraint, and it is the transformed dual objective. So we have dual objective and we have the constraint. So this is how we transformed our problem to this problem, and this basically gives some intuition how we can deal with the duality in the general case, which is just framing this other way around as in the general case. It won't take much time. It's just that if the Braynius theorem conditions are followed and you have p equal to 2, let's say p equal to 2, and you have infimum over gamma So what you can see that in the general case we have same kind of thing here. The except this inequality, but our primal problem was this, which was in our case was minimizing gamma ij Cij. Primal problem is linked with this, and the dual problem here, as in the decomposition into f and g, is being followed here. So there's some link behind, and particularly this inequality is very straightforward to prove, because let's say you have some f and g which follows this thing, then easily f d mu plus g d mu is basically f plus g d gamma. Why? Because we know the first marginal is mu and the other marginal is nu. So if we evaluate d gamma on f and integrate on rd, rd cross rd, we have integral rd on f d mu, and for g we can say integral over rd on g d nu. And so in that case, from this inequality it holds that this is less than equals to integral of x minus y whole square d gamma, and if you take supremum here, infimum here, you get this inequality. So, and the fundamental theorem of optimal transport says that if the Braynius conditions are followed, and so the fundamental theorem says that for p equal to 2, if the Braynius conditions are followed, then this instead of this weak duality, you have a strong duality where this infimum and the supremum are equated, and together with the Braynius theorem and this strong duality, you have the fundamental theorem of optimal transport. So that was all about the optimal transport, about all the motivation behind optimal transport, how it deals with the matrix structure of the distributions, and how the transport maps are associated with the notion of distance between two measures or two distributions in an underlying space which respects the underlying matrix structure. So that was all about the framework of optimal transport. That's all. So for your case, I must understand that these all things were very